Today we're going to talk about chemical analysis. There are two kinds of chemical analysis that are useful. One is called qualitative analysis, and in qualitative analysis you're just trying to determine the qualities of a substance. That's kind of where the word part comes from. What elements are present is the question that you're asking when you're doing qualitative analysis. You're just trying to find out what's there. We're not going to spend a lot of time on that now, but as time goes on, you'll start to develop some techniques for figuring out what's in there. What we're interested in right now is quantitative analysis. Once the qualitative analysis has been done and you know what elements are in the compound, then the question becomes how much of each element is there. In other words, there's a quantity involved, and so that's why quantitative analysis has that same word part that quantity does. When you're doing quantitative analysis, often the result is that you end up with something called percent composition. And percent composition is a list, actually. It's not one number. It's at least two. It's a list of the percentages by mass, not by moles, but by mass, of all the elements that are in the compound. Here's an example problem. We've got 0.5462 grams of a compound, and there's isolated from this mass 0.1417 grams of nitrogen and 0.4045 grams of oxygen. So we know how many grams of each are there, and we know the total. We have two questions. First is we have to find the percent composition. That's our first job. And then we also need to find out if there are any elements present. Well, we can actually answer the second question first. It's easy to do. If you add 0.4045 to 0.1417, you're really close to 0.5462. So, yeah, there's probably nothing else present there. So the percent composition is just going to be a list of what percent of this compound's mass is nitrogen and what percent is oxygen. Let's solve the problem. This compound contains 0.4045 grams of oxygen. That's out of a total mass of 0.5462 grams of compound. If I divide here, I get 0.7406. Now, to express this as a percentage, what I really want to do is multiply by 100%. So that gives me 74.06%. That tells me what percent of this compound is oxygen. Since the only other element here is nitrogen, well, the rest of it's got to be nitrogen. So 25.94%, which is 100 minus 74.06, is the nitrogen content. Or alternatively, I could say 0.1417 grams of nitrogen divided by, again, the total, 0.5462 grams, and get myself the same percentage after multiplying by 100. Another way of getting percent composition is from the formula. This is called theoretical percent composition. You calculate it from the formula without actually any data. Here's what it's useful for. If you have quantitative analysis and it's given you a percent composition for a real compound, knowing the theoretical percent composition can make a match for you. It can help you select which formula goes with what I actually have done quantitative analysis for. How do you do it? Well, the first thing you want to do is find the mass of each element. You do that by taking the subscript, which is the moles, times the molar mass. Then you want to find the molar mass of the entire compound. Well, if you found the mass of each element, summing that up will give you the molar mass of the compound. Then the last thing you do is find the percent composition. And so what you'll do is you'll take the answers from 1 and divide each one by the answer from 2, and that will give you the percent composition. Here's an example, N2O3. It's got two elements in it. One's nitrogen. Nitrogen has a subscript of 2, so that means 2 moles times nitrogen's molar mass, which is 14.007 grams per mole. And that tells you that you have 28.014 grams of nitrogen in your compound. I can do the same calculation for oxygen. 3 moles, because the subscript is 3, times 15.999 grams per mole. That's the molar mass of oxygen. And that gives me 47.997 grams of oxygen. Well, the sum of these two is the total mass of the compound, or the molar mass of the compound, and so that's 76.011 grams. Now, to find out what percent is nitrogen, 28.014 grams divided by 76.011 grams. And then I'll multiply by 100% to give myself a percentage. This works out to 36.855%. Notice that I'm keeping all 5 significant figures. Oxygen's, well, 47.997 grams divided by that same total molar mass, and then expressed as a percent. And this is 63.145%. Quick mathematical check. If If I add these two percentages together, I should come up to 100%, and I do. A useful thing that can come from quantitative analysis is determining the formula of what you've got here. Now, it's not always easy to get the exact formula. That might require a couple of steps. But for some compounds, all you need is the empirical formula. And even for others, the empirical formula is a great step. Here's what the empirical formula is. It comes from the word empirikos in the Greek, which means pertaining to experience. And that means it comes from our quantitative analysis. Here's what it really is defined as. It's the simplest whole number ratio of atoms of different elements in a compound. So we know that all formulas have subscripts. We want to find out the smallest whole number ratio of those subscripts, basically, and that's the empirical formula. How do we find it? Well, here are the steps. First of all, divide the masses of each element by the molar mass of that element to find the number of moles of the element. If you have raw data, you just take mass of nitrogen, for example, divided by molar mass of nitrogen. Once you've got the quantities of moles for each one of the elements, you find out which one's the smallest. Pick the smallest of the mole quantities and set that sort of equal to 1. And say all your ratios are based on that. And then divide all the mole quantities by the smallest of the mole quantities. That will give you some numbers. They'll either be whole numbers. If you're within a few hundredths of a whole number, you can round right to the whole number. Otherwise, they'll be simple fractions, like 3/4 or 2/3 and 1/3 or something like that. Very simple fractions. Nothing complicated. If they're not whole numbers, then multiply the resulting fractions by the same whole number, multiply all of them by the same whole number, until the ratios are all in whole number form. So, for example, if one of my ratios was 1.5, then I would want to multiply everything by 2 to get rid of the half and make them all whole numbers. And then once you have whole number ratios, you express them as a chemical formula. So each one of the ratios that you have becomes a subscript in a chemical formula. Probably best to learn this by example, so let's try one. Here we have a compound. We have a 1.5246 gram sample of it. It has nitrogen and oxygen in it, and we know that it has 0.7117 grams of nitrogen. Our job is to find its empirical formula. The sample of the compound that we have has 1.5246 grams total. We know that out of that, 0.7117 grams are nitrogen. So the remainder has to be oxygen, and the difference is 0.8129 grams. So that's the amount of oxygen that's there. Now our first job is we have to turn all the mass quantities into mole quantities. So I'll take my 0.7117 grams of nitrogen, and I'll change that into moles of nitrogen by using nitrogen's molar mass, which is 14.007 grams per mole. This works out to 0.05081 moles of nitrogen. I'll do the same thing for oxygen. 0.8129 grams of oxygen divided by oxygen's molar mass, which is 15.999 grams per mole. This works out to 0.05081 moles of oxygen. Well, I'm supposed to divide by the smallest one, but they're both the same. So here's what that means. It's a 1 nitrogen to 1 oxygen ratio. So my simplest formula, my empirical formula, is N1O1, or just NO. Let's try this one. Here we have percent composition data. This is not too hard to work with, because if you assume you have 100 grams of the compound, and it's all ratios, so you can pick whatever quantity you want, percents are just grams. It's a little tricky because we don't know how much oxygen is there, but if it only has sodium, sulfur, and oxygen, which we got to assume, then we can just by subtraction figure out how much oxygen is there. Let's find the compound's empirical formula. Assuming I had 100 grams of the compound, I would take that 100 grams and subtract the amount of sodium and sulfur that I know are there, which is 32.37 for the sodium and 22.57 for the sulfur. And this leaves me the mass of oxygen, which is 45.06 grams of O. Now, I need to find moles quantities. So I'll do the sodium first. It's 32.37 grams, and sodium's molar mass is 22.99 grams per mole. And this leaves me with 1.408 moles of sodium. Next I do sulfur, 22.57 grams of sulfur. The molar mass of sulfur is 32.064 grams per mole. And when I do this calculation, I get 0.7039 moles of sulfur. And I now know that 45.06 grams of my compound is oxygen. Oxygen is 15.999 grams per mole. And this calculation gives me 2.816 moles of oxygen. Well, most of you can see where this is going probably by just looking at the ratios and figuring out what the whole numbers are going to be. Let's do the calculation though. 1.408 moles of sodium would be divided by the smallest number of moles, which is 0.7039 moles of sulfur. So my sodium-sulfur ratio comes out to be 2.000. Now, that number is within a few hundredths of a whole number, so you can round that off and we'll say that that's 2. Sulfur, we've established that as 1 by using it as the smallest number. And then if we take 2.816 moles of oxygen and divide by 0.7039 moles of sulfur, we get an oxygen-sulfur ratio, and this works out to 4.001. Again, that's really close to a whole number, so we can just round straight to a whole number. So it's 2 sodiums to 1 sulfur to 4 oxygens. So to make that into a formula, Na2, sulfur 1, oxygen 4 is our simplest formula. After recording this, I decided that I should go back and throw in another example because we really haven't seen a time where our ratio doesn't work out to whole numbers, and it'd be nice for you to know how to do that. So I made up a new example here. We have a compound that has nitrogen and oxygen in it. It's got 0.5219 grams of nitrogen and 1.490 grams of oxygen. And our job here is to find what's the empirical formula. So our strategy is, first we have to find out how many moles of nitrogen we've got. So I take 0.5219 grams and I'll convert that into moles by using the molar mass of nitrogen, 14.007 grams per mole. That works out to 0.03726 moles of nitrogen. I'll do the same thing for oxygen, 1.490 grams of oxygen, and I'm multiplying by the inverse of oxygen's molar mass, 15.999 grams per mole. This works out to 0.09313 moles of oxygen. Well, the smallest number of moles here is the nitrogen moles, so we're going to establish that as 1 and find the ratio of oxygen to nitrogen. So it's 0.09313 moles of O for every 0.03726 moles of nitrogen. Here's what I get. 2.499 moles of oxygen per mole of nitrogen. Well, that's not close enough to round it to 2 or 3. In order to round to a whole number, we have to be within a few hundredths of that whole number. So then we have to look for a simple fraction. Well, here's our simple fraction. This is approximately equal to 2.5 or 5/2. Now, we can't really write a formula that says N1O5/2 because this is reflective of atoms and there's no such thing as a half of an atom. So how we deal with that is we take both of the subscripts and we double them. In this case, if it was 5/3, we'd triple them. If it was 5/4, well, we'd quadruple them. But we want to get rid of the denominator by multiplying by a whole number that does it. So 2 works in this case. So multiply nitrogen by 2, that's N2. Multiply oxygen subscript, 5/2 by 2, and we get 5. And there's our simplest formula. In reality, when a compound is analyzed, it usually isn't possible to just take the 2 elements and separate them like you would ideally do. In some of the problems that we've been working on, we've sort of assumed that that can happen. But often what happens is the elements get separated not by putting them by themselves, but by putting them into separate compounds, into different compounds. And we know those formulae, and so we can use what we know about stoichiometry to work backwards and figure out what the original compound was made of. This is called indirect analysis. Here's an example. Let's say you wanted to analyze a hydrocarbon. So a hydrocarbon is something that contains hydrogen and carbon. And you can actually do this with compounds that contain other things besides just hydrogen and carbon, like something that contains hydrogen, carbon, and oxygen, for example. If you had a compound like this, you can analyze it in this kind of a setup. So here's what happens. You put in one chamber here of this device the compound that you want to analyze. You pump in pure oxygen from this end, so not air, but pure oxygen. And you heat it up so a reaction takes place. The products of combustion are going to be, we all know this probably, CO2 and H2O, if it's just a hydrocarbon. Well, in this chamber, the next chamber that the exhaust goes through, there's a water absorber, like something that's in the desiccators that you've used in lab, that attracts moisture and takes it out of the exhaust stream. So the water gets absorbed by this water-absorbing material. And then it passes from there into a third chamber that's got a carbon dioxide absorber. And that carbon dioxide absorber can remove the carbon dioxide from the exhaust stream. And there might be some unburned oxygen, but that'll just go out the other side. So if we burn up all the hydrocarbon, then that means the carbon that was in this compound will end up in CO2 because there's no other compound on the product side that has carbon in it. And the hydrogen that came from this compound will end up in water because there's no other compound that contains hydrogen on the product side. And then oxygen, you'll have to deal with that some other way if there's oxygen in the compound. So this is indirect analysis. So how do you use the information that you gain? Well, the first thing you want to do is you divide the number of grams of each of the product compounds by its molar mass, and that'll give you moles of that product compound. So like carbon dioxide, for example, divided by carbon dioxide's molar mass, you know how many moles of carbon dioxide you have. Second thing you do is you use composition stoichiometry to find the number of moles of each element that was captured in the product compound. So for example, if you had carbon dioxide as one of your product compounds, you know that every mole of carbon dioxide contains 1 mole of carbon. So if you know how many moles of CO2 you have, you also know how many moles of carbon you have. But all of that carbon came from the original reactant that you're trying to analyze, and so therefore you should be able to use that to figure out a formula. So once you've got that figured out, you can just proceed like you normally would to find the empirical formula of the compound. So here's an example, indirect analysis. A compound contains only carbon, hydrogen, and oxygen, so 3 things. So that means its formula would be like CXHYOZ. And here's what we know. When you combust 5.048 grams of it, you get 7.406 grams of carbon dioxide, 3.027 grams of water, and our job is to find the empirical formula. Well, let's do it. Well, here we have our data reproduced. We've got 5.048 grams of the compound, 7.406 grams of CO2 as a product, and 3.027 grams of water as a product. The first thing I want to do, I think, is I'm going to find out how many moles of carbon are present, and I'm going to do that by pursuing the strategy that was outlined in the last few slides. So I take 7.406 grams of CO2, and I divide by the molar mass of carbon dioxide. Molar mass of carbon dioxide is 44.009 grams per mole. And when I do that, I'm going to end up with moles of CO2. But I'm going to take this one step further because I know that every 1 mole of CO2 is going to give me 1 mole of carbon, so this will ultimately give me moles of carbon that were in my original compound. When I do my arithmetic, I find I get 0.1683 moles of carbon. That's the amount of carbon that was in the original compound. Well, I can do the same thing for water. Take the grams of water, divide by water's molar mass, which is 18.015 grams per mole. And now my mole ratio is slightly different because a mole of water doesn't give me a mole of hydrogen. It gives me 2 moles of H. When I do this arithmetic, I get 0.3361 moles of hydrogen. Now, the thing that we have to deal with at this point is how much oxygen do we have? And we can't do that from stoichiometry directly here because we have oxygen in both products. Both CO2 and H2O contain oxygen. So here's what we'll do. Let's find out how many grams of carbon 0.1683 moles is. Molar mass of carbon is 12.011 grams per mole, and now we put the moles on the bottom, so that cancels. And this will tell us how many grams of carbon were in the original compound. 2.021 is the answer. We'll do the same thing for hydrogen. If we had 0.3361 moles of hydrogen in our compound, and hydrogen is 1.008 grams per mole, this will give us the grams of hydrogen in the original compound, which is 0.3388. So if I take 5.048 grams, which is the total mass of the compound, and I subtract from that the mass of the carbon and the mass of the hydrogen, I will get the mass of the oxygen. When I do that, I get 2.688 grams of oxygen. So what am I going to do with that? Well, 2.688 grams of oxygen can be converted into moles of oxygen, because oxygen is 15.999 grams per mole. This works out to 0.1680 moles of oxygen. So here are our 3 mole quantities. There's moles of carbon, there's moles of hydrogen, and there's moles of oxygen. The smallest one is 0.1680, but that's almost exactly the same as carbon. So carbon and oxygen are 1-to-1 ratio, and 0.3361, well, you can see that's about double of 0.1680. You can do the arithmetic on your calculator, but it'll give you this conclusion: carbon 1, oxygen 1, hydrogen 2. So our formula would be CH2O. When you have an ionic compound and you find the empirical formula, you're done, because the empirical formula is the only formula that exists. In an ionic formula, all you're doing is calling out what is the ratio of one ion to the other in the crystal of that compound. But for molecular compounds, the smallest whole number ratio, the empirical formula, it might be the actual molecular formula, or it might not be, because there's more going on than just a simple ratio. For example, think about a compound NO2. That has the simplest formula, NO2, as well. But N2O4 has the same simplest formula. The empirical formula for both of these compounds is NO2. But they're not both the same. N2O4 is quite a different compound from NO2. However, we do know that molecular formula subscripts are always going to be whole number multiples of the empirical formula subscripts, like we saw in the last example I just had up here, NO2 and N2O4. Double the 1 here and you get a 2. Double the 2 and you get a 4. We could have another compound, N3O6, that would also have the same empirical formula, but here it's tripled, and you could keep going, theoretically. So how do you find the molecular formula? Well, first of all, if you have the empirical formula, calculate its molar mass. Second, you'll have to have the actual molar mass. Either you'll have to be given this or given some information that allows you to calculate it. And you divide the actual molar mass by the empirical formula's molar mass and round this to a whole number. It'll always come out really close to a whole number unless you've made a mistake. Well, that whole number is what you multiply all the subscripts in the empirical formula by to get the molecular formula. Here's an example. The empirical formula of hydrazine is NH2. Its actual molar mass is 32 grams per mole. What's its molecular formula? Well, first I want to find what's the molar mass of NH2. One nitrogen is 14.007, 2 hydrogens at 1.008 each. If I add that all together, I get 16.023 grams per mole. The actual molar mass is 32.0, so when I divide that by 16.023, you can see that this is going to be really close to the whole number 2. So hydrazine is NH2 with the subscripts all doubled, which gives me N2H4.